What are grounding considerations for high-voltage transmission? Have you ever wondered how high-voltage transmission systems keep everything safe and running smoothly? Grounding is a key part of that equation. Let's break down the important considerations for grounding in these systems. First off, system grounding is essential. This means connecting the neutral point of transformers or generators to the earth. It helps stabilize voltage during normal operation and sets a clear reference voltage. When faults occur, proper grounding allows fault currents to flow safely to the earth. This lets protective devices quickly detect and isolate any issues. Next, we need to talk about fault current management. High-voltage transmission lines must be grounded to handle large fault currents, like single-phase to ground or three-phase faults. Grounding conductors and electrodes need to be sized correctly to carry these currents without damage or excessive voltage rise. Transient overvoltage control is another important aspect. Grounding helps limit temporary overvoltages caused by imbalanced faults or switching operations. Effective grounding reduces line-to-ground voltages on unfaulted phases, preventing insulation damage and equipment failure. When it comes to grounding conductor installation, for overhead lines, grounding conductors are installed along the transmission line structures. This provides a low-impedance path to earth. The size and number of these conductors depend on the expected fault current magnitude and system voltage level. Shielding and cable grounding are also vital. Shielded control cables associated with high-voltage equipment must be grounded properly, often at both ends. This helps divert induced electric and magnetic fields to ground, reducing transient voltages and electromagnetic interference. Equipment grounding is necessary too. Metal parts of transmission equipment that do not carry current, like enclosures and support structures, must be grounded. This prevents hazardous touch voltages and ensures safety for personnel. Temporary personal protective grounding is crucial during maintenance. When work is done, temporary grounds must be applied to de-energized conductors and equipment. This protects workers from accidental energization or induced voltages. Coordination with protective devices is essential. Grounding systems must work alongside relays and circuit breakers to ensure fault currents are detected and cleared quickly. This minimizes equipment damage and reduces outage duration. Substation grounding grid design is another key consideration. These grids are designed to spread fault currents safely into the earth, keeping step and touch voltages within safe limits for personnel. Lastly, grounding practices must comply with electrical safety standards and utility-specific requirements. These standards may specify maximum allowable temporary overvoltages, minimum conductor sizes, and grounding configurations. In practical terms, grounding for high-voltage transmission requires careful engineering analysis of fault current levels, soil resistivity, and system configuration. This ensures grounding systems protect equipment and personnel while maintaining system reliability. Selecting appropriate grounding electrodes, conductors, and connections is vital for effective fault clearing and reducing transient voltages.